All right, friends, we're back and we're talking about gas. So we're going to be discussing gas theory today, which is part of Unit 3, Area of Study 1 of VCE Chem. We're going to be talking about two main dot points. We're going to be talking about gas pressure, which is sort of its definition and how it's measured. We're going to be talking about PV equals nRT, better known as the ideal gas law. And we're going to be discussing some calculations with these aforementioned values and expressions. The first thing we're going to discuss is gas pressure. And we're going to begin this discussion by conceptualizing gases. So I want you to imagine we have a finite area. Okay, this could be some sort of container, like a beaker or something. And inside we have gas particles. So as we know, they're going to be fairly spread out, kind of going all over the place. Some are going to be traveling over here, some are going over here. This Donny's moving towards here, this guy's going towards here. They're just sort of chilling, having a good time. Okay? Now, this would be what we would characterize as a low pressure state, which means that essentially the gas particles are not colliding with a lot of force and with not a lot of frequency. If we compare it to something like this, though, where say we have a bunch of particles, they're all moving really rapidly, and they're going all over the place, and they're colliding and they're just kind of jiggling all over the place, and there's so many particles, it's everywhere. That's going to be a lot higher pressure. So this gives us a bit of a hint on what pressure indicates, right? We know that in this situation, the gas particles are not colliding with a lot of force, and in this situation, they are colliding with a lot more force. And when we think about pressure, we usually think about a lot of things trying to burst out, or if you have like a Coke bottle and you shake it up and the pressure starts to build in the bottle, you can tell that the gas wants to escape. So that kind of leads us to our definition of gas pressure, which is really about the force exerted divided by the area. And that kind of leads us to two main points about pressure, which is that in order to increase pressure, you can increase the force or you can decrease the area. And that kind of makes sense. If you have a gas trapped in a certain amount of area and you decrease the volume of that area or decrease the volume of the container it is in, the pressure is going to increase. And this leads to a very important relationship that is explored further in the ideal gas law, but we'll touch upon it here just now, which is that pressure varies as inversely with volume. What that essentially means is that if you increase the pressure, you're going to have an effective decrease in volume, and vice versa. If you increase the volume, you're going to decrease the pressure, decrease volume, increase pressure. Okay? And this is kind of the fundamentals which underpins a lot of our discussion of gases later on in VCE chemistry. So we talk about this relationship between pressure and volume a lot more when it comes to equilibria. But it's important to understand now and when we go further on to talk about the ideal gas law, because it's a really important relationship, and oftentimes calculations involving gases involve manipulating one of these two variables. So we've described pressure in a qualitative sense already, but there are ways we can describe it in a quantitative or numerical sense as well. There are three main units that are used to describe pressure in VCE chemistry. The main one, and the one that's used for the ideal gas law, which we'll be talking about shortly, is kilopascals. We also have millimeters of mercury with the units mmHg. And you also have atmospheres, or ATM. The way you convert between them, and the one that's written in your data book, is that 100 kilopascals is equal to 750 millimeters of mercury, and that is also equal to 0.987 atmospheres. So you can kind of play around with these values to try and find something in kilopascals. A quick example would be if I knew that I had 1500 millimeters of mercury pressure, and I wanted to convert that to kilopascals, I'd first divide this by 750, which knows I have 2 times 100 kilopascals, which is equal to 200 kilopascals. You kind of mix and match these different types of measurements to get what you need. But most of the time, you will be going from these different measurements of millimeters of mercury and atmospheres to kilopascals to eventually plug in to an ideal gas law formula. Now, with our discussion of pressure out the way, we can talk about the main formula that you're going to be using whenever you have a gas law question, which is the ideal gas law, which is expressed as PV equals nRT. Now, the best way to kind of unpack this equation is to go through each of the values or variables individually. So P, as we've been talking about before, is pressure. And as I said before, it is very important to remember that it is measured in kilopascals. So if you have a unit like one of the other ones I was talking about previously, you need to make sure you convert it to kilopascals first before you plug it into your equation. V is pretty standard, it's just volume in liters. Nothing new there. N is the number of moles, and that again is just measured in moles, pretty standard as well. R is a constant value, which is the ideal gas law constant of 8.31. And then T is temperature. But it's important to remember that this is temperature not in degrees Celsius, but in Kelvin. Now, Kelvin is basically just the degrees Celsius plus 273. So if you have a degree Celsius value, so you are at 25 degrees Celsius, that is the same thing as 273 plus that, which is 298 Kelvin. Okay, so this is also written in your data book for easy access. So you don't have to memorize this conversion. You just need to look at your data book whenever you need to use it. Okay, the final thing we're going to discuss is some calculations involving the previous concepts we've already talked about. One thing to cover before we get to those calculations is the molar gas constant. Molar gas constant, which states that the volume of an ideal gas at SLC, is very important, and SLC is equal to 24.8 multiplied by the amount of moles. Now, the way that this 24.8 number comes from is SLC is defined as 25 degrees Celsius and 100 kilopascals. If you plug these values into PV equals nRT, you get a value which means the volume of a gas is always equal to 24.8 multiplied by the amount of moles of the compound. And so you can use this as a shortcut when you know that a gas is at SLC, usually the question will tell you, to rather than putting in all the values of SLC into PV equals nRT, to just use this 24.8 number to convert between moles and the volume. Okay, so now that we've discussed all the tools and the concepts necessary to tackle some equations, we're now going to go through an example calculation. So I'm just going to write out this question real quick, which is what volume of methane measured at SLC will combust to release 4 times 10 to the 4 kilojoules. Okay, so the first step in a question like this is to establish the equation we're going to be using, all right? And this will help when we talk about stoichiometric procedures and things like that. But in this case, we don't necessarily have to do that because it's just asking about how much methane we could use. So we could use an alternative method, but it's important to get good principles and things like that. So I'm just going to write the equation out as so. So this is a standard complete combustion reaction. So I'm going to write the unbalanced version first. Plus H2O. Now balancing across, this will be like that. And the delta H value will be, according to the data book, negative 890 kilojoules per mole. Okay, so pretty self-explanatory. This is the first step. Okay. The second step now is going to be utilizing this kilojoule number and this kilojoule number to figure out how many moles we have of methane. So I'm just going to go 4.0 times 10 to the 4 divided by 890. Now this is another reason why I said you don't necessarily need this equation. We could have just started with this number and got to this step. But if there's a second part which asks about utilizing the mole ratios to find out how much water is produced, then it's handy to have this equation here as well. So that's going to give us a value approximately 44.9 moles. And then from there, it's really as simple as using the molar volume constant. So that's the V is equal to 24.8 times N, which is equal to 24.8 times 44.9, to give us a final volume of 1.12 times 10 to the 3 liters. Now, if the question then asks, all right, you have this value, now calculate the amount of H2O released, then that's when the equation would come in handy. So if we go back up here, we would see that we have 44.9 moles, and we know that for every 1 mole of methane, so these are moles of methane, for every 1 mole of methane, we produce 2 moles of water, so it would be the amount of moles of water is equal to 2 times the amount of moles of CH4 or methane, which is equal to 2 times 44.9, which is equal to 89.8 moles. And then you could find the volume of this, or you could find out how many grams it is by using the molar volume constant that I used previously, or by using N is equal to M on big M. So that's kind of the fundamentals. Sometimes you have to use PV equals nRT, and so that will be the next example I show you now. So here we have a bit more of a difficult question that incorporates a few more tools and strategies that we need to use. So essentially the question is asking us to find the volume of a product when a fuel is completely combusted. So as I mentioned before, the first step usually that you want to do is to write the equation out. And this is very essential for this type of question where we are going to have to utilize mole ratios in order to get the correct answer. So as such, I'm going to write the unbalanced equation first. So complete combustion produces carbon dioxide and water. Chuck the states in as well. Liquid, and then balance across. So we have three carbons here, 3 carbons there. We have 4 hydrogens to make 4 times 2 to make 8. And we've got 6 plus 4, 10 oxygens. So we have 5 as the coefficient for the oxygen here. And that's our balanced equation. Now the second thing is we're going to find the number of moles of propane and then use that to find the number of moles of carbon dioxide using mole ratios. So we're going to know the moles of propane, or C3H8, is going to be 800 grams over the molar mass of propane, which is 44. And we're going to give us a value of 18.2 moles. Okay, then we know that the ratio between the propane and the carbon dioxide is 1 to 3, meaning for every 1 mole of propane, 3 moles of carbon dioxide are produced. So we can just multiply this number by 3. So the N, or the moles of CO2, is equal to 3 times NC3H8, which is the same thing as 3 times 18.2, which is ultimately equal to 54.5. So obviously this has been rounded moles. Okay, So this value is rounded, and that's how we get to this point. So now that we have the moles of carbon dioxide, we need to find the volume. Now, before we could use the molar volume trick at SLC to quickly find the volume of the gas given the moles. But because we're not at SLC, we're at 60 degrees Celsius and 200 kilopascals, we actually have to use PV equals nRT. So if we scroll down a little bit here, we go 3 PV equals nRT. Now, some people prefer to put in the values and then rearrange the equation. I like to rearrange the equation first to isolate for the variable I'm looking for and then move on. So V is what we're looking for. So I'm going to divide both sides by P to give us nRT on P. Now, one point I am going to make here, okay? T is in Kelvin. So we're going to go 60 degrees Celsius is the same thing as 273 plus 60, which is equal to 333 Kelvin. Okay, so we already have the pressure value in kilopascals, so then we can just put in all our values. So we get the moles. We get the moles from this over here. We go 54.5 multiplied by our constant value, which is 8.31, multiplied by our temperature value of 333 Kelvin. Finally, all divided by the 200 kilopascals up here. So we go 200, plug that into a calculator, and you should get a value of 755 liters.